Last week, we started to talk about systems, right? So what is a system? So a system is, can be viewed as a process in which, input signals are transformed into output signals, okay? Now, different systems will produce different outputs in response to the same input. So if you want to describe a system, you will need to characterize the relationship between the input and the output, okay? So a system is characterized by the relation between its input and output, okay? And we gave some examples of this last time, right? So in these examples here, you can write out an explicit mathematical equation describing the relation between the input and output, okay? Now, in many cases, we can often describe systems or study systems as interconnections of simpler subsystems, right? So they can either be in series, in parallel, or a combination of both, or even in a feedback form, okay? So one advantage of studying or designing systems as a interconnection of subsystems is that now we can focus on designing specific functionalities of these subsystems, which is easier than designing the whole complex system as a whole, okay? All right. Now, last time we started to talk about, some different properties of interest that we may have that help us categorize systems into different types, okay? So in particular, we talked about, systems with or without memory, and we still need to cover properties such as, invertibility, causality, stability, time invariance, and linearity, okay? And the last two probably is the most important for our course, okay? All right, so let's start one by one, right? So we already mentioned last time that, a system is memoryless if its output at a given time depends only on its input at that time, okay? So here we have a few examples, right? So for example, here y of n equal to 2xn minus xn squared. We can see that the output at time n, right, this output at time n depends only on the input at the same time, okay? So similarly, if you have an input-output relation like this, where y of t is equal to r times x of t, you can see that the output at time t depends only on the input at time t, and therefore this system is memoryless. Now, any system that depends on an input or output other than the current time is a system with memory, right? So it could depend on some past input, or it could also depend on some future input, right? So we gave a few examples of this last time. So one is the accumulator, right, where the output at time n depends on the input from minus infinity up to time n. So the output at time n depends on all of the past input. So for delay, the output at time n depends on the input at the previous time. And for a capacitor, it's more or less like the accumulator. Right? It integrates all the inputs from time t and before. All right, so this is a system with or without memory. Right? A system is memoryless if it depends only on the input at that time, and it has memory if it depends on the input at any other time as well. Okay? All right. So the second property is invertibility. Okay, so what does it mean for a system to be invertible? So in particular, we say that a system is invertible, okay, if distinct inputs lead to distinct outputs, if distinct inputs lead to distinct outputs. So for example, suppose you have a system, let's say a system like this, right? And with inputs, let's say 0, 1, or 2, 0 is mapped to a value 5, 1 mapped to some value, let's say 7, and 2 mapped to some value 3. Okay? So in this case, this is an example of the case where distinct inputs give you correspond to distinct outputs. Okay? So when distinct inputs lead to distinct outputs, this means that whenever I give you the value of the output, I know what was the input, right? So if I tell you that the output is 7, you know that the input is 1, okay? So if this is true, right, if distinct input leads to distinct outputs, this means that you can always find an inverse system that maps the output to the corresponding input, right? Okay. So a system is invertible if distinct inputs lead to distinct outputs, meaning that there exists an inverse system, right? There exists an inverse system such that this inverse system helps you convert each output to its corresponding input, okay? So therefore, if you cascade this inverse system with the original system, then taking any input, you get the corresponding output, and the inverse system converts it back to the original input, okay? So a system is invertible if there exists an inverse system such that when cascaded with the original system, it yields an output that is equal to the input, okay? So the interconnection, the cascade of a system and its inverse system forms an identity system, okay? So a system is invertible if you can find an inverse system such that when cascaded with the original system, together forms an identity system. Okay. So here we have two examples. Okay, so these are two examples. So in this example here, our system produces an output y of t that is equal to 2 times the input, okay? So an inverse system would then be a system that produces an output that is equal to 1/2 of the input. So when you go through this first system, the input is multiplied by 2, and then when you go through the second system, it's multiplied by 1/2, giving you the original signal. Now here we have another example in discrete time. This is the example of an accumulator, right? So here the output yn is equal to the summation of the input from -infinity up to time n, okay? Now for this system, you can find an inverse system like this, right? So the inverse system produces an output w that is equal to the input at time n minus the input at time n minus 1, okay? So if you substitute this inside, right, if you subtract this with the summation up to time n minus 1, what you're left with is x at time n. So the inverse system to an accumulator is this difference of the input. So this system here, because you can find an inverse system, therefore the accumulator is invertible. Now, in practice, you would see invertible systems in many places. Right? So for example, in a communication system, you would take the message you want to transmit, you convert it into a code word that can be sent through the channel, and then you have a decoder that converts the code word back to the message that you wanted to send. Okay? So in this case, the encoder and the decoder are examples of a system and an inverse system.